So in this last video we're going to be looking at percent yield, and this is a way for us to determine how much product we should have made versus how much product we actually made in a laboratory setting. So two items are going to go into this percent yield. One of them is our theoretical yield. This is the maximum amount of product that could have been formed from the reactants. And you would get a theoretical yield by actually doing the math, looking at a balanced equation, looking at how much product did you put into the experiment, or sorry, how much reactant did you put into the experiment, and actually doing the math. This is and looking at how much product you could have made, how much you should have made. And then we have our actual yield, and this is the amount you truly do get when you perform the lab. Normally those aren't going to be the same. Very seldom will you get 100%, and we'll talk about some reasons why here in the next slide. So your percent yield is a ratio of those, and to get your percent yield you're going to want to take the actual amount that you get in the laboratory setting and divide it by how much in theory you could have made. When you divide those, then you're going to multiply that by 100 to move your decimal place to actually get your percent. Now your percent yield is kind of a measure of how efficient you were when you carried out the lab. So when you're looking at some things that can affect your yield, and we will do some at least one lab where we look at our percent yield, some things that you want to keep in mind, because these are things that can lower your amount of product that you get. First of all, sometimes you don't let your reaction go to completion. So if you stop too early, where not 100% of your product has had a chance to be made yet, that's going to lower your results. If you started with impure reactants, so you want to make sure that the chemicals that you're using are pure chemicals. If you have any competing side reactions, and sometimes this isn't always controllable, especially maybe in a high school lab setting, but things like the water vapors in the air can sometimes react with the chemicals that we're using in a lab, and so we might have a side reaction going on that we didn't intend on happening, but that can take away some of the reactant that we meant to use for a different purpose, and so that's going to decrease the product. Also, we could lose product when we're filtering or transferring. So if you have to take your product from one container and scrape it and put it into a different container before you weigh it, if you don't get 100% of that, you scrape every single little piece of it out, then you are going to have less product when you weigh it on the balance. So you want to be really careful there that you do transfer everything from your container if you have to transfer containers. And then of course just not careful measuring. So if you said that you put 5 grams into your experiment, but really it was only 4.8, or really it was supposed to be 5.2, if you didn't measure it carefully to begin with, then that's going to change the percent yield at the end. Alright, now we're going to do at least 2 of these 4 practice problems together, and for this first one we are decomposing calcium carbonate, and we want to know the theoretical yield of the calcium carbonate first. Okay, the next practice problem is going to ask us to take that theoretical yield and to do a percent yield with it. But first we need to know how much can we make. So we are going to have 24.8 grams that we are heating up, and when we do that we're going to be breaking it apart into carbon dioxide gas, which is going to be more difficult to trap since it's a gas, but we are going to get this solid left over. And so if we were to truly do this, in theory we should be able to calculate how much calcium oxide we make. So we want to convert grams to moles, and we do that with a molar mass, and you should be putting in all of your units and all of your substances. So the molar mass is 100.1 for calcium carbonate, And then in order for us to go from calcium carbonate to calcium oxide, we need to do a mole to mole ratio. Now this is already a balanced equation, so 1 mole of the calcium carbonate is equal to 1 mole of the calcium oxide. We're almost there. We have moles, but of course if it's a lab situation we're not going to be able to use moles on our balance. We're going to want to know how many grams of calcium oxide we had, so we're going to convert this to grams. The molar mass of calcium oxide is 56.1. Now if you were to plug all of this into your calculator, you're going to get 13.9 grams of calcium oxide. That is in theory how much you could produce if you had 24.8 grams of calcium carbonate to start with. Because remember, some of that mass is going to the carbon dioxide. Practice problem number 2 is kind of a connection with problem number 1. We want to know the percent yield for this problem. So I am telling you that when we actually do this lab, you get 13.1 grams. That's how much you get on the balance when this is all said and done. This is the amount we originally started with from practice problem number 21. Sorry, from practice problem 1, we started with 24.8 calcium carbonate. We ended with 13.9 grams. So this work has already been done in practice problem number 1 for you. What we're going to do is take our theoretical of 13.9, the actual amount, and we want to do a percent yield problem for that. So percent yield says we do actual over the theoretical, and that is 13.1 grams over the, in theory, 13.9 that we could have gotten. We want to multiply that by 100 when we're done. So when you do this, your grams are going to be canceling, so there's no unit. Percent yield doesn't have a unit like moles or grams or anything like that, but we do want to keep significant digits, so our answer should have 3, and that's going to be 94.2%. So not too bad. You lost a little bit, but it wasn't too much. We were still about 94%. Now in this practice problem, this is going to be combining what we just did in problems 1 and 2 only into one problem. So you are given that you are starting with 50 grams of the silicone dioxide, and it is telling you that this is how much you produced. So this is your actual right here, but the question is what your percent yield is. Now in order to do the percent yield, we need to know the actual, which we have, check, but we also need to know the theoretical yield. So the theoretical yield is what we did in practice problem number 1. We're going to take the 50 grams of the SiO2 and we're going to be converting that into, over here, grams of our silicone carbide. So that is what we're trying to see how much we should in theory be able to produce. So you can go through the steps. We'll just jot some of them in here. Now you should be putting in your amounts, your numbers. You should also be writing in the formula, what formula you have. So we want to convert that to moles. We're going to want to do a mole to mole ratio. And lastly, we want to convert the moles of SiC into grams. Balanced equation, we can get the mole to mole ratio. We have molar masses here and here, and you should be able to then get your mass of silicone carbide or silicone monocarbide, and then you can do a percent yield. Okay, actual divided by theoretical and then multiply that by 100. So that's practice problem number 3. Now practice problem number 4 goes a step further. In this practice problem, you're given the amount of 2 reactants, that you have 15 grams of nitrogen, you also have 15 grams of hydrogen, and it tells you what your actual is. So this is the actual amount that we get when we do the lab, but we want to, again, we have to know the theoretical yield, and in this case, to do the theoretical yield, we need to know which one of these, the nitrogen or the hydrogen, is the limiting reagent, so that we know which one is going to run out first, which one determines the amount of product we get. So we'll be working through practice problem number 4 together, but if you want to give it a shot and work on limiting reagent, it would be good practice for you. But we will definitely be taking a look at this one in class. I don't even think I could fit it all in this space. It is going to take a little bit of work since you have all the steps of limiting reagent you have to work through. But definitely practice problem number 3 is your responsibility, so have that one done the next time that I see you. And if you work a little bit on practice problem number 4, that would be excellent. So it'd be great practice.